This next lesson is on power. And power is the rate at which work is being done on an object. So when we talked about work in the last lesson, we didn't actually care how long it took us to ride our bike to the top of the hill or to lift that box into the back of the truck. We just wanted to know how much energy did we use. Now with power, we're going to take time into consideration. So to kick off this lesson, we're actually going to stop and watch a short video clip on work and power. It should be a summary of what you learned in your lesson on work and also a preview of what we're going to hit in today's lesson.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They are adding energy to the clock at a rate of 2.5 watts. You'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.
So hopefully that was a good review, and here we go with the lesson. If you are exercising and you're getting tired, it is not because you are doing work. It is because you are generating a lot of power. And power causes tiredness. So if you ever wondered why you get so much more tired when you run a kilometer than if you walk a kilometer, it's because you're putting out a lot more power, pushing yourself along at a lot faster rate. So that is the key idea behind today's lesson, is how fast you're doing the work. So, as you might guess, the rate at which work is done, power is work over time. So it's how much work am I doing in how much time, that is my power output. Now, power is measured in two different options. If you think about what work is measured in joules and time is measured in seconds, so that would be a joule per second, which you're perfectly free to use. But we've redefined this as actually, we've called that a watt. So W stands for watt. So don't confuse that with W for work. This is W as a unit, and this is W as a variable. So W for watts is what we're going to measure power. So that would be 1 joule of energy used up every second. Now, fortunately for us, power is also a scalar, so we don't have to worry about vectors, and that's going to make our life just a whole lot more simple. So let's take a look at our first example. An electric motor is used with a pulley and a rope to lift a 650 Newton load from the road up to a height of 12 meters. Now this 650 Newtons, we would say this is how much the applied force is. It also, when we talk about a 650 Newton load, this is the force of gravity on the object, but we have to overcome the force of gravity in order to lift it. So this is the force we're going to use in our work equation. And we want to lift it to a height of 12 meters, so that's fine. There's my distance. And this job is done in a time of 11 seconds. So here's my D distance, here's my T time, and we want to know what is the power output of the motor. So to find power, I've got power is work over time. And I know work, I can just calculate work using force times distance. So instead of calculating that separately and then putting the number in, I'm just going to put the formula in. So work equals force times distance. And then I'll keep this over time on the bottom. And then I need to actually plug in my numbers. So I've got force, which is my 650 newtons. I've got my distance, 12 meters. And I've got my time, 11 seconds. So I'm going to pull out my handy dandy calculator and see what I get. So here we go, 650 times 12. Divided by 11 tells me I have a work of 709. That would be 3 sig figs, so I'll stop there, 709. This would be either joules per second or 709 watts. So that would be perfectly fine as my final answer, 709 watts. But we have a little note down here that says, an often used unit to measure power is the horsepower. And they talked about horsepower in the short video clip you watched at the beginning. 1 horsepower is equal to 750 watts. So sometimes we are asked to convert from watts into horsepower so that your quote-unquote clients could compare with 1 horse. So let's see what we get. 709 watts. In this example, the motor would have a horsepower of, well, I want to convert 709 watts. I'm going to use this to create my conversion factor. So I have watts on the top, I need watts on the bottom, and I need horsepowers then on the top. And then just plug in your numbers. So 1 horsepower is 750 watts. So I would just pull up my calculator again and divide by 750 to get my answer. So 709, I'm just going to use, actually in this case, the answer divided by 750 tells me I've got 0.945 horsepower. So almost a full horsepower. In other words, this motor is doing the work of almost 1 horse. And maybe that depends on what horse you're using, if it's actually equivalent to a horse or not. Let's take a look at another example. A 60-kilogram girl runs up a flight of stairs, 3.32 meters high, in 2.6 seconds. What is her power output in watts? So why don't you pause your video, maybe label the information. Remember that work done against gravity, I'm going to need Fg equals mg. And maybe I could even plug that, substitute that into my formula. So pause your video, then come back. Okay, so I've got, again, power equals work over time, and work is force times distance. I'm moving over time, and in this case, the force that I'm using is the force of gravity, so I'm going to actually just sub in mass times gravity times distance over time. Let's see if I can plug in my answers, or my numbers. So 60, that is my mass. G, I know, is 9.8. This is going to be my distance, and here's my t, time. So I've got 60 times 9.8 times 3.32 divided by 2.60 seconds, and pull out your calculator, see what you get. So as you can see on my calculator, I've got a power output of 750.8, so 751 then watts as my final answer in watts. Now part B asks me if 1 horsepower equals 750 watts, what's her power output in horsepower? So I would take my 751 watts times 1 horsepower over 750 watts. Again, same conversion factor that I used in the previous question. Take my answer in my calculator and divide by 750. As you can see, it's almost exactly 1 horsepower. So I could put 1.00 horsepower. This time it's a little bit more than 1 horsepower, but 1 is close enough. So again, as was said in the video, the horsepower was originally defined by a guy named James Watt, who was looking for a way to describe the power of his newly invented steam engine in terms that people accustomed to using horses to do their work could understand. If you want to market something to people, you got to give it to them in terms they get. So that's why sometimes you'll be asked in the question to convert to horsepower. I think every single time this comes up on a quiz or homework assignment, or sorry, on a quiz, not necessarily in your homework, but on a quiz, they will give you that 1 horsepower equals 750 watts. So you don't have to have that memorized, but you do need to know how to use that piece of information. Example number 3. How long would it take a 10 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? So now we're kind of going in the backwards direction. We're wanting to know, we're starting with horsepower, and we're needing to get to time. How long? So that's what this question is asking. Time equals what? Remember that horsepower is a measure of power. Here I've got 500 kilograms. This is going to be my mass. And we're lifting it up to 30 meters above the ground. This is my distance. And I need to solve for time. So I'm going to develop my equation the same way that I did in the last time. I'm going to say power is work over time. Work is force times distance. We'll keep that over time. And in this case, the force we're having to overcome is gravity. So I'm going to use mgd over time. And maybe I'll rewrite this down here because I'm going to need to solve this now for time. So in order to get time by itself, I'm going to multiply. I need to get it off the bottom. So I'm going to multiply top and bottom by time, sorry, both sides by time. So power times time, or time times power. So if I move this up, I know, let's go up here. I've got now power times time equals mass times distance mass times g times d, and I need to get time by itself, so divide out your power. So I get time equals mgd over P. In order to actually solve this now, I need to plug in the correct numbers, and I need to make sure I'm in base units. So this 10 horsepower needs to be converted using my opposite conversion factor. So now I need to do horsepower on the bottom, watts on the top, 750 watts over 1 horsepower. So this is going to be 7,500 watts total. So we're going to plug in those numbers then. So mass, again, 500, G 9.8, distance 30, and power 7,500. Pull out your calculator, plug that all in, see what you get. So in my calculator, I've got a final answer of 19.6 seconds. Whoop. let's take this to the next step. Power can be measured in kilowatts or megawatts, just like we can convert any other of our base units. So again, these should be on your formula sheet. That a kilo is 10 to the 3, that mega is 10 to the 6, the same way that those prefixes work for a kilometer or a megameter, if you like. So sometimes we need to be able to convert these just like we would any other base unit. So, example number 4. The power of a light bulb is the amount of electricity it consumes in 1 second. How many joules does it consume every second? So a 40-watt bulb, for example, uses 40 joules of electrical energy in 1 second. So 40 watts is 40 joules in 1 second. Watt is joule per second. So what is the power rating of a bulb that consumes 4,200 joules of electrical energy in 70 seconds? So again, pretty straightforward. We're just looking for what is the power, but in this case, we are given the amount of energy that it consumes. This is the work done and the amount of time in seconds. So this is pretty straightforward. Power equals work over time is 4,200 joules in 70 seconds. You can do that. 4,200 over 70, maybe not in your heads, but on your calculator, gives me 60 watts. I'm going to put this dot here so that I get 2 sig figs. If I don't have the decimal point, this is only 1 sig fig. So this is 60 watts, which would be 60 joules in 1 second. Example number 5, a microwave is rated for 1.2 kilowatts of power. So now we've got this kilo coming in. 1 kilo is 1,000 watts. You may need to convert that. It is running for 6 minutes. There we've got our time. So we have power, we've got our time. How many joules of energy does it use? So again, that joules of energy, that's how much work is done. So I've got my equation, power is work over time. And to solve this for work, which I'm looking for, I'm going to multiply both sides by time. So I've got power times time is work, or work is power times time. But in order to actually use this equation, I need to get everything into base units. So I'm going to convert my 1.2 kilowatts into, well, let's see, 1 kilowatt, I was told, is 1,000 watts. And again, I want to set this up so kilowatts cancels kilowatts on the top, cancels kilowatts on the bottom. And so this is just equal to 1,200 watts. And my 6 minutes, I need to convert that into seconds. So I'll multiply by, let's see, minutes on the top needs to cancel minutes on the bottom, and seconds on the top. 60 seconds in a minute. 6 times 60 is 360 seconds. Plug that into my equation to find work. So work equals 1,200 watts of power times 3,600 seconds. Again, type that into your calculator and you get 432,000 joules. And again, if I wanted to, I could convert this from joules into kilojoules, just like I have kilowatts, so 1,000 joules. Let's just do this for the sake of, it's 1,000 joules is 1 kilojoule. So then this would be 432 kilojoules of energy. Most of the time we don't have to use those conversions unless the question actually asks us for it, but it's handy to know how to do it if you need it. So that is just converting using our normal conversion prefixes. In the next question, we are given a kind of funky unit called a kilowatt hour. A kilowatt hour is a measure of energy, and here is why. In the previous question, we multiplied to find energy or find work. We multiplied, here we had power times time. We multiplied watts and seconds because that's how we get to joules. So power was in watts times time in seconds. So you could also say that a joule is equal to a watt second. We just multiplied watts times seconds and got into joules. So if I multiply something like kilowatts, there's power, and hours, that's time, then again, power times time should give me energy. Power times time gives me work. Power times time gives me energy. So kilowatt hour is another way to measure energy. That's key. Even though it has watts in it, it's a way to measure energy. So how many kilowatt hours does the microwave in the previous question use? So again, we can use this to set up a straight up conversion factor. I'm going to go from 432,000 joules, and I set up my conversion factor. Again, joules on the top needs to cancel joules on the bottom, and I want to end in kilowatt hours. So 1 kilowatt hour is 3.6 times 10 to the 6 joules. Set up your conversion factor and then type that in on your calculator. So I've got 432,000 times 1 over 3.6 to the power of, no, not to the power of, times 10 to the power of 6. Remember to use your scientific notation. And that gives me 0.12 kilowatt hours. 0.12. The joules is going to cancel, and I'm left with kilowatt hours as my units. Okay, so again, just some practice with this conversions. You might not have done this for a while, but set up your conversion factor so units on the top cancels units on the bottom, and they usually, again, will give you this on a test or quiz. You don't have to have this memorized. Note, kilowatt hours is a measure of energy, not power. It's energy times time, which is equal to, power times time, which is equal to energy. A hot dog takes 4,000 joules of energy to cook. So here I'm looking at energy. This is my work. If a microwave is rated at 800 watts, there's power. How long, looking for time, will it take to cook a hot dog? So I've got power, work, time. Here we go. Power equals work over time. I'm going to solve that for time, so I'm going to multiply it by time to get it out of the denominator. So I've got power times time equals work. And then I'm looking to get time by itself, so I'm going to divide out power to get time equals work over power. And then everything is already in the units that fit together, so joules and watts, those are fine, those are my base units. So 40,000 joules divided by 800 watts gives me, let's see what I get. 40,000 divided by 800 gives me 50 seconds. Again, to get to 2 or 3 sig figs, I could do 50 point, that's 2 sig figs, 50.0, there's 3 sig figs seconds as my final answer. This is how they calculate the amount of time that is printed on your hot dog packet if you want to know how long you need to microwave it for. Believe it or not, they're using physics. Note, large microwaves are rated at 1200 watts. Small microwaves are usually rated at 800 watts. How long would a large microwave take to cook the hot dog? So instead of having my power be 800 watts, I'm now going to use power of 1200 watts, but it's the same equation as above. So time equals still the 40,000, but this time divided by 1200. Okay, pull out your calculator again and type it in. 40 divided by 1200, 40,000 divided by 1200. This time it only is going to take 33.3 seconds to cook your hot dog. So again, if you've ever cooked a hot dog in the microwave, the packages always say microwave oven times may vary depending on what the power rating of your microwave is. A special version of the power equation we get if we are moving at a constant speed. So we know for any scenario we have power equals work over time, and we know that work equals force times distance over time. And you may recognize this distance over time should be familiar. Distance over time is actually just velocity. So if I substitute out distance over time, this ends up being just force times velocity. Now it is important that my velocity is a constant speed. This originally power equation will work whether you're moving at a constant speed or not. But this version with velocity in it, or speed in it if you like, only works if we're moving at a constant speed. So we're going to use that in example number 8. How much power are you generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at 12 meters per second? So there again is your constant speed, 12 meters per second. We've got a constant force. Here's my force, here's my speed, and I want to know how much power. So power in this case is force times velocity. Force of 32, velocity of 12. 32 times 12, my calculator says, is 384. 384 watts. So again, if you're given a constant speed, you don't actually know the distance or the time, although you could say, well, actually, I'm going 12 meters in 1 second, so I could put in 12 and 1 if you like. But when you're given a velocity in the question, it's easier to remember that velocity is distance over time. So part B, if you wish to go faster, will that require more or less power? So let's think about that. Power is force times velocity. So if I keep the same force, but I want to go faster velocity, that is going to require a higher power. So to go faster, you are going to need more power. And does pedaling faster make you more tired or less tired? I don't know how many of you ride bikes, but you definitely get more tired when you go faster. So again, more power equals tired faster. More tired, tired faster, whichever way you want to look at it. Okay, so that is it for this lesson. Again, big idea, power is the rate of doing work, how fast your work gets done, and we can relate that to things like horsepower, which came from James Watt, who is trying to relate that to something people would understand when he created his steam engine. And we can also relate that to force times velocity if we're going at a constant speed. Good luck on your homework and your quiz.